All right. I think I will just skip this one here and go to functions of random variables. So this is a little bit about error propagation as well. So if you have also in your project you use a certain result and you then do some type of operations on this result. Start with your final result. What are then the standard errors after you've done all these operations? And so the way to do that is given here basically. So if you go from x to y by adding a constant, of course the expected value of the mean is increased with that constant, and the variance stays the same. So your standard error also stays the same. If you multiply with a constant, of course you multiply the mean, but the variance is now multiplied with the square of that constant. If you have then a linear function like this, obviously this would then be your expected value, so the mean, and also your variance you can calculate them through like this. All right. If you have normally distributed random variables and you calculate with those, and you have some type of linear function, then also the result of that is normally distributed and the variance is this. So this is exactly the same as the previous slide, but now random variables are randomly distributed. Okay. So important for you to realize that some of these rules work, and also when you make reports, it's important to think a little bit about what is the error I can expect, and don't just start putting numbers in your calculator into the computer and come up with 6 or 7 digits when you report on your data. Okay, so think about this and think about this error propagation type of rules. Okay, so an example of this. We have a manufactured part, length x1, width x2. They're normally and independently distributed. We have 2 centimeters as the first mean, and this is the standard deviation, 0.1 centimeter. Mu5 is 5 centimeters, and then the standard deviation is 0.2 centimeters. The mean and variance of the parameter. Okay. So this is 2x1 plus 2x2. So the expected value of this would be 14, right? So 2 times 2 plus 2 times 5 is 14. And the variance would be 0.2. Is that right? Would the variance be 0.2 square centimeters? Can you check? Is anybody willing to check if this is correct? What would you need to do to calculate the variance of this? Some people do this internally, other people start calculating. Yeah, so what do you get?
0.2.
0.2. And how do you do it?
Take the first sigma 1 squared times the coefficient in the y equation, and the same for the second one, and then you get 0.2.
Okay, so you did 0.1 squared times what?
2 squared.
Times 2 squared, so this is this coefficient. And the same for, this is mu2. It says now mu5, but this is makes more sense if this is mu2, so that you can use this for x2 here. So you do the same, and that gives 0.2. All right. And now we want to determine the probability that the parameter of the part exceeds 14.5 centimeters. As both of these are normally and independently distributed, we know that this y will also be normally distributed. So we can use now, once again, the normal distribution, and we want to use the normal standard normal distribution. So we calculate the probability of y being bigger than 14.5 is the probability of y minus the mean of y divided by the standard deviation of y, which if we then put this in, the value 14.5 minus 14 being the average of y, expected value of y, divided by the standard deviation on y, which would be the square root of this here. Okay. So that gives us then the z value, the limiting z value, for which we have to see what the probability is of z being higher than that value. And so if you look that up in the tables, that should be 0.13. Okay? So this is the probability then. All right? We have to be concerned with independency to be able to do this. So in principle, before you apply this, you should look at the correlation between the variables. So if there's a large correlation between some of these random variables, you cannot actually use these simple rules, and you have to make corrections for that. So then you have to use this covariances. So in case you're faced with such a case of not having independent variables, where you have a large correlation, then it's good to use this type of correction for the variance. If we have nonlinear functions, what you can do is then to calculate the expected value by filling in the mean. So you're transforming a mean by using, or you have some results which you transform by a nonlinear function. So then the expected value, of course, is putting that mean into that function, the nonlinear function. The variance you calculate by taking the derivative of the function to the variable, squaring that times the standard deviation of the original variable squared. Okay, so this is what you need to do. And so you have to look at how dependent that nonlinear function is on a change in the random variable and square that, and that gives you then the variance. Okay. So we have also an example on that one, and I'll allow somebody to walk us through it, as this is a good exercise. It saves my energy. Would you like to do it? Okay. Yeah. You would have also liked to do it, but
example to the formula, and that's 102,000 square watts. So that's a square watt. So to get the standard deviation, the root of that would be 220 watts. Yeah, at 20 amperes.
Okay. All right. Thank you. So, of course, we have to take a derivative with respect to the current. Huh? Why is that?
Because it's swap-related.
Because yes, and the current is a random variable, and so the resistance here is a constant. Okay. So if we want to then apply the nonlinear function rule, we need to, of course, take derivative with the random variable, which is the I, right? And then calculate this term. All right, so that's how to do it. This can be quite useful if you want to have an estimate of the standard deviation if you have a nonlinear function applied to your random variable. All right, so and of course you can make this if you have a number of independent random variables and you take a function of that, you have to do the summation to get to the variance of the standard deviation squared times the partial derivative of the function to the random variables. Okay, so this is something you can certainly do. All right, let's have a 5 or 7 minute break.